Hello, today we are going to discuss skipgram model to create neural network embeddings. We will be discussing this from the viewpoint of word embeddings, that is for text datasets. Skipgram mainly helps generate word embeddings by predicting surrounding words from a given word in a sentence or in an actual text. It works in a manner that there is a window, just like we see only a few words when we are reading. Skipgram leverages a context window in which it creates relationship between words. Those discovered relationships are used as inputs and expected output in a neural network. Within that window, each word becomes a central word or a target word against which a context word is predicted. Skipgram is effective for learning representations of infrequent words that are defined by emphasizing more on frequent words as context. If you have the word apple, if you see that in the surrounding words you have the words iPhone, iPad, these sorts of technological terms, then you realize that the word apple is not really a fruit in this context. It is the company Apple. How are these embeddings actually learned? Let me make my image a bit smaller. Okay, from each relationship, where in the relationship we have a reference or target word and then we have a context word. So in the input we provide that reference word as one hot encoding, and then that one hot encoding helps us select the particular embedding vector for that word. Word embeddings form a matrix where each row refers to a vector representation of a word. The selected embedding for the reference word becomes an input for the neurons of the output layer. Then the output of the output layer is compared with the context word. The computed loss, which is likely the cross entropy loss, helps in the backpropagation, and during the backpropagation all the weights and biases of this part of the neural network as well as the content of the embedding matrix will be updated. So for every word that we read in the text, a number of context words will form a pair with the reference word, and that way each pair helps in updating the weights and biases of the network and updating the embeddings. This is the neural network part of the skipgram model. But how are those pairs actually constructed, where the first word becomes an input and a context word becomes an output? So the first word can be beautiful, the context word can be flower, or the first word can be operating, the context word can be systems. The skipgram model operates over a window system. That's a sliding window. So if you have a window of certain length, you keep moving it over the text. Just like when we read, we actually look at certain words. We don't look at the entire text at a time. So basically, skipgram model helps predict surrounding words based on the target word to learn effective word embeddings. I should mention one item in the skipgram model. The target word actually refers to the first word or the word which is in the center, and the context words refer to the words in the vicinity, in the surrounding. For example, if we consider on to be the center word here in this context, target word, then the next word and the word after that, the word you have before the center word and the word before that, those words that are marked in yellow, they become the context word. The word target refers to the expected output in a neural network. We are not referring to that. The expected output is the context word, that is these yellow words. So if on is the center word, then A will become an expected output. Also against on, mat will become an expected output. Anyway, skipgram model helps in efficient representation learning by predicting context words. This whole process of skipgram works using a sliding window mechanism. So you read the whole text in documents or in entire book by moving this sliding window. As we read natural language in our daily life. This sliding window is defined by a fixed size spanning certain words that we will discuss soon. The neural network setting you saw, that is a shallow neural network. That means that we don't have deep layers there. The reason is that we don't want the model to learn complex relationships in the deep layers. Rather, we want the model to learn the relationships in the embedding matrix so that the representation of the words, that is the embeddings, become very accurate. Therefore, skipgram is a shallow model, that is, it has fewer layers compared to many other deep learning models. The idea is to keep the model simple and not make it too complex that the other part of the neural network starts learning too much. One may have deeper layers if the primary purpose is something different than embedding generation. Let's discuss an example. Let's say that the text we have is the cat sat on the mat, and the sliding window size is 3. In a skipgram model, when we say that the sliding window size is 3, we mean that we have a center word or a reference word, and we take 3 words after that and 3 words before that as the windows. So practically that window will have a maximum of 7 words. 3 words after, 3 words before the center word. Every word in the text will become a center word at some point. In the text, the first word we have is the, which is in index 0 of words. There is no other words before the word the. The 3 words after that are cat sat on. So these are the context words for the word the. So we have the, then we have cat sat on. These are the 3 words. Practically, the pair for the input and output of the neural network will be the cat, the sat, and the on. These are the generated pairs. Let me make the window a bit bigger. Okay, now we have generated all pairs associated with this particular word, the. Now the next word that will become our center word is cat, which is in index 1. For cat, the 3 words after cat are sat on the. There are some words before the word cat as well. There are not 3 words, but there is 1 word before cat. So our context words for cat would be the, sat, on, the. Note here that this word the repeats in the context. Our pairs should be cat the, cat set, cat on, and cat the. So these are all our pairs. So there are 4 pairs for the word cat. Our next word is set. Now we know that the next 3 words would be on the mat, and there are 2 words before set. Since our window size is 3, we pick up those 2 words in the context as well. So for set, we will have the cat on the mat as our context words. So for set, we have the cat on the mat, and all the pairs should be set the, set cat, set on, set the, and set mat. Again, notice that we have the word the repeated in the same context. After the word set, we have the word on, and for on, we have 3 words before on and 2 words after on. For the word on, which is at index 3, the context words are the cat sat, the mat. And these are the pairs: on the, on cat, on set, on the, and on mat. Note here that this on the and this on the are the same, which is fine. The neural network gets more trained when we have repeated pairs. After on, we have the word the, and for the, our context words are cat, sat, on, and mat. Therefore, the pairs are the cat, the set, the on, and the mat. After the word the, we have the word mat, for which the context words are set, on, the. So this is on the set, but this is the same set on the. So for mat, it will be mat on, mat the, and mat set. Pretty amazing, isn't it? I'll bring everything on the same screen. So the pairs for the neural network would be these pairs, these pairs, these pairs, these pairs, these pairs, and these pairs. So all these pairs are generated with window size of 3. This text could be huge. It could be an entire book. So the words you have in the entire book can be provided in a words list. And then you can move your sliding window over the text just like we have described here. All the pairs will help you train the neural network model we just saw a few minutes before. This is how skip-gram model works. So here I have written the full code for skip-gram modeling and some testing. In the beginning, we need to take a look at the data we have so that we understand the testing part well. So we'll be looking into the content of sample text.txt. We have this text: the cat sat on the mat, the dog lay on the rug, the cat chased the rat. Slowly this text actually went to the trees in the backyard. The bird flew over the trees, the bird sang in the trees, so on and so forth. So it started with cat, dog, barking, chasing, mat, rug, rat, these items, and then it moved to bird, trees, sang, playing near the tree. So it's about the bird and the tree in the end. I'll provide a link with this text as well as this code. I'm importing necessary libraries. Then I'm checking for the GPU. This code is suitable for both GPU and CPU. Here we are loading the entire text, converting the text into a list of words. So in this function, we create the vocabulary. We return two data structures. One is a mapping between unique words and their IDs. And this one is providing words against the IDs. So this is a map between word to its ID or index. And this is a mapping between index to corresponding word. This part is the part that actually creates all those pairs as we just discussed a few minutes ago. Here the default window size is 2. That means for a center word, 2 words forward and 2 words backward will be used as context words if they're present in the text. So this data actually provides all the pairs we have. This is the neural network part. Okay, notice here that it's very simple as we discussed before. We have the embedding layer which has the vocabulary size, that is the number of rows you have, and the embedding dimension is number of columns you have. Then we have a linear layer, and that linear layer is of however many dimensions you have as input, and the output of that linear layer is number of words you have. So the center word index comes in from the embedding layer. You pick up that particular row, that means the embedding vector for that certain center word, and then that embedding vector becomes an input for the output layer you have. The output is directly returned. So this is a shallow neural network, not really a deep neural network as we discussed before. Here we are creating batches of certain batch size. Then we have written a function named train where actually we do all those epochs. We pick up the batches, and for each of the batches we create center words and context words from the pairs we have. Then the rest of the process is just like a regular feed-forward neural network. Here the criterion computes the loss. And since this is a classification problem, we are using cross-entropy loss because we are predicting a particular word that falls under classification territory. So neural network-wise, it's not really complex, but the concept itself was novel when it first came up. We are loading the text, tokenizing it using the functions we wrote, creating the vocabulary and the reverse lookup, preparing the data with window size of 3. Our embedding dimension is 10. That means in the embedding space we have 10 columns. Then we create an instance of our neural network, which we are calling skip-gram model. We call the train method that we looked into. We are running it for 150 epochs. So the epochs will reduce the overall loss, and at some point we see that the loss is not decreasing much. In the embedding space we have 35 rows, 10 columns. 35 rows would mean that we have 35 unique words in the text we saw. We are printing all the words, like the embedding for the word the embedding for the word cat, the embedding for the word set. All of them are printed here. Now in this part, we are looking into the embeddings of two words, cat and dog. You can change them. And we find that the cosine similarity between the word cat and dog is 0.48 based on the embeddings generated. Also here we write a function that finds out the nearest neighbors, top k similar words of a given word. Of course, we need all the embeddings of all the words, so we are providing that to the function. So this function would return us top k, where actually in this context we have set k as 5. So let's say who are the nearest neighbors of the word mat. It is showing us that the nearest neighbor of the word mat is next, cat, dog, slept, sat. And in the first part of the text we actually had the word mat, we had relevant words like cat and dogs in the surroundings, so those words are actually closer words, so this is the cosine similarity. We are also doing a few more tests. Here are those test samples. You can test this using your own data. If you have 1000 documents, you can write another program to copy the content of those 1000 documents sequentially in one file. Then you can use this program. I will upload this code on GitHub and provide a link in the description section. Scriptgram modeling is an amazing algorithm widely used for its simplicity as well as its effectiveness in capturing the contextual similarity between pairs of words. Thank you very much for watching. See you soon in another video.